presently in this lab called ISMO in abbreviation, Institute of Molecular Sciences at Orsay. It's a kind of new lab because it was created only in January 2010 from the merging of other labs. Okay, this is basically what I put in my abstract. I probably will cover the first few up to here, down to here, but probably not the other ones. But that will be enough, I think. So everybody have seen this kind of thing before. You can find different names. Aromatic infrared bands is fine for me. Question is that they are seen everywhere. It's very important, observable nowadays with new instruments. As an example, this current way to present visible against infrared images of galaxies, and of course astronomers are able to recover important information about galaxies that way. This is another example. Okay, but what about what's behind this infrared emission? The only aromatic molecule, as far as my knowledge, is a benzene molecule. Going back to this paper in more than about 12 years ago. Okay, and the rest is just maybe not speculation, but something which doesn't actually got a real identification. Okay. The kind of situation in which we observe these emissions shown as an example here is Earth-Edge Nebula, and here you have a question mark in that paper that are pH precursors of small hydrocarbons in these PDRs, and this is based on the spatial correlation between the observation of C2H and the AIB emission bands. Okay, behind that you can speculate. Okay, the first thing I will talk about is this. We have access to through a platform at the Synchrotron Soleil near Paris at a beamline which is sufficient for doing high resolution in the far infrared range. And the name of the beamline is called L. And thanks to this facility, is possible to task efficiently problems like the low frequency vibrations of these large molecules. And why is it interesting? Is because these low frequency vibrations are much more species specific because of the skeleton motions than the main transitions which are specific to bond, basically CH bond or CC bonds, aromatic CH or aromatic CC. These are kind of things in which the signatures are present in pH. But if we want to assign, really identify ones, we have to find something more specific. That's one way. In addition, it allows to get information on the anharmonic interactions between various modes. And this is an essential knowledge to input into the modeling of the whole pH emission. That's another interest of doing that. So another thing is that it's going closer to a region, spectral region where many spectroscopic instruments are really champion. Okay, this is the synchrotron itself. This is a Fourier transform spectrometer. And of course, you don't see the light, but you have the logo of the beamline. And one of the things which have been possible to do recently, together with the Institute in Rennes and people of Soleil, of course, is to set up a slit nozzle expansion chamber in which we can do direct absorption thanks to the FTIR. And of course, the cooling obtained allows to see things, simplify the spectra actually. This is just a few examples. One is, this is naphthalene. It's not written, yes, it's naphthalene at room temperature. This is one low frequency band that's between 7 and 800 wave numbers. Because of the room temperature, there are many lower frequency modes which are populated. And this is the origin of all these odd bands. It's an A-type kind of bands. And you can see progression like those, this, not progression, but sequence like here or there, involving different vibrations. And this is a comparison between purely theoretical calculation, starting from DFT kind of calculations, is in a way quite remarkable kind of overall agreement, but in detail is quite different. For instance, this series has a wrong sign as a one compared to what is really observed. I mean, it means that the anharmonic coefficients is just a different sign. Okay, so this is a kind of information. Oh, this is to stress this coupling constant between mode 46 and mode 13 is positive in experimentally, while it is predicted negative. And there is some overall agreement, but with some discrepancies as well. This is an example of the low temperature slit jet spectrum, where you can see fairly well resolved and well fitted spectrum. Okay, starting from naphthalene and being interested to the sensitivity of low frequency modes to the real structure, we have looked for a number of derivatives like azulene, which is an isomer, or if you introduce a nitrogen atom, quinoline or isoquinoline. And you can see that basically DFT works well to predict the position of the band. I won't comment more. One can, for instance, play with looking at what happens on a given kind of mode, like butterfly, or chair, or scissors, how the frequencies changes in the different species. You see that there is a pretty good similarity in this kind, as well as in that kind. Here it's a bit different, of course. It's normal because of mass effect of nitrogen. What?
Go back to the
previous one, yeah.
You said DFT. Which one is DFT calculation?
Ah, the one in black. It's a simulation using the rotational constants, ABC, kind of.
Yeah, they probably
With room temperature. Yeah. DFT provides just one frequency, and we add on it this kind of standard calculations to have a better comparison. Yeah, that's just kind of artificial, of course. This is another example. It's not naphthalene, but it's two rings, but this time with a CC bond in between the rings. And things becomes to be different. There are more degrees of freedom, including, for instance, this is an out-of-plane molecule. So the two cycles are not in the same plane. There is about 40 degrees according to the literature in the difference of the angle of the two planes. And again, DFT does a pretty good job, except for some modes. This is not clearly obvious in that case, but there are other molecules in which it is much. Every very low frequency modes can, where there is a kind of tunneling effect or things like that, they cannot be predicted by DFT as normal. You see, of course, it's not a surprise. This mode has completely different frequency as well as those one. Okay. Now, change of setup. We are more interested in a family of molecules, of kind of cousin molecules. They have something in common. They have aromatic CH and CC bonds, and there are spectra behind that. Than a given one. That's another way to attack the question. So, a way to form a whole family of PAHs, and is well known, is to burn anything, carbonaceous thing, something which contains carbon atom. And best accessible is just small hydrocarbons, like ethylene or acetylene. And in addition of that, it's the only so far properly working model, proposed model for explaining pH formation in space. In the circumstellar envelopes, there are high temperature chemistry, and starting from acetylene, for instance, you can this kind of models of this high temperature chemistry predict the formation of pH. It's not so surprising. And another aspect is that in these flames, when you burn something, if the stoichiometry is not well adjusted, you get solid particles. You get a soot. And obviously, there must be some connection between pH and soot, because you will, as you will see, soot appears when pH decreases. Okay, well, we have tried to make experiments according to these things, these ideas, and of course also when you have carbonaceous grains, you can think they have some connection with the soot structure, and it's known that when they are illuminated by UV light, we produce pH, so there is the other way around. Okay, so we have set a combustion flame and a vacuum. This is a kind of summary of the kind of work we have been doing. This shows an ethylene flame, and with a quartz cone, you come is kind of well-known setup in combustion community. It's a laminar flame, which means that you go from the burner itself outwards. You can probe at different distances, according to the duration of the where you are in the flame. This cone, the products present in the flame at that point are extracted, and then I will explain you how. We have been doing two-dimensional kind of spectroscopy. In one direction, we measure the mass thanks to a mass spectrometer. In the other direction, we measure the UV spectrum by resonant two-photon ionization. Okay, this is how a bit more detail about the setup. This is a burner, McKenna kind, kind of reference in this field. And from the quartz cone, we arrive in what we call a thermalization chamber, in which we inject helium flow. And this flow is pushing the material through a nozzle, and this nozzle is again skimmed to enter a low pressure a low pressure chamber in which the species are ionized by resonant two-photon ionization. And these are the acceleration electrodes of the time of flight. Okay? So this is not really an in situ analysis of the flame, because we are not really measuring in the flame, but it's a kind of probing in which we can do, with which we can do really online measurements. And we can vary something and see what's happening really online. Okay, this is how it looks like. The combustion chamber is there. This is the time of flight, and in between you have the other pieces of equipment. This is again from closer view of the combustion flame, the combustion chamber. You can see a little bit of a flame here. So the window, and this is the same thing, and this is a ethylene flame, very soothing. The red color comes from the soot. Mass spectra. This is a set of mass spectra, different wavelengths. So 208, 248, 266, 282, you see that there are changes. It's not too much of a surprise, because every pH has its own spectrum. There is no reason why they should all observe at the same place, and something like that. For instance, there is only one in which you see benzene. This is because benzene, the spectrum of benzene near UV is composed of sharp bands. And if you are not on one of these sharp bands, you see no benzene at all. although it's there. If you have a shorter enough wavelength, you see the precursor gas. And you also, then all the other things should be something related to pH. You can recognize numbers like C10H8. This is naphthalene. Should have something to do with naphthalene. Then one has to prove by scanning the laser. And this should have to do with phenanthrene or anthracene, and so on. Okay, this is how it works. So then we scan, we get all the data in a kind of single shot, single scan. We record at every wavelength step a full mass spectrum, as I was shown on the previous slide and two dimension in 3D representation. And then you try to analyze the spectral shape on every mass. And that way you find the spectrum of benzene and a number of derivatives. These are all derivatives of benzene. There are more than that. This is toluene. This is phenol. This is etanyl. No, it's ethyl. Yeah. Usually methyl acetylene. No, I'm sorry. Vinyl. Yeah. This is one with a ethyl radical, but it is isomeric of these xylenes, and xylene also has 3 isomers. So it was not a simple task to recover out of that spectrum what's the real content of that. And the 3 species which are really present are those 3. Only 2 of the isomers of xylene are present. And here you have both NOH and as cresol and methyl para-cresol because they are in para position. Okay, and so forth. That will be it with the unsaturated aliphatic branch here and there, 1 here and 2 there. And you see, for the real identification, you need a set of to look into reference spectra, and if they don't exist, you have to make yourself or find another way. Okay, a little bit more styrene, again with naphthalene. With benzene derivative, as a benzene derivative, indane, which is well known that it is formed in these combustions. And then we have a number of other identification, so the spectroscopy for 2 to 4 rings molecules. Naphthalene, of course, comes first, and you can see that you have different kinds. Methyl naphthalene, we observe the 2-methyl. This is ethanyl, and then we go to 3 rings, phenanthrene. Anthracene was almost not significantly present, and it was not possible to should be much less abundant because it was not possible to recognize. This molecule is a five-membered ring. Methylphenanthine, and with 4 rings, pyrene, of course, very condensed, very compact, and also these 2 isomers. This is tetraphene and tetrahelicine, which is out of plane in that case. Okay, a number of species. You have a full list here. Some of them are which are not completely definite, are presented in different characters. And what we can tell from that is that results are quite similar, I would say, with the results which have been obtained in different flames. Of course, not if you change hydrocarbon, you change a bit the chemistry. But it's most of the time, apart from 1 or 2 studies, they're always measured offline by completely different chemical techniques. So this is all kind of new and original. To take kind of not a full summary, but a special aspect of what is taking out of this study is that a large number of unsaturated aliphatic chains are branched on the aromatic network. And this is probably a clue aspect for the chemistry itself, for the growing up of larger to larger pHs. And if we go beyond, that's what will happen is that all pHs will disappear and we get completely stacked with soot particles. So a way to show that is we selected a few mass and basically you can make an assignment for everyone knowing the wavelengths and you scan from the distance to the burner because the burner itself can be moved, the cone is fixed, and you see this kind of distribution, and there is nothing else. And if you look into the flame, you see it's all red, and it's because you have everything has been transformed to soot. You form solid phase species. This is just to mention that we can go to higher masses, and we can also see all the radicals which play a role in the beginning of this chemistry if we use a single photon of higher energy because these species have a higher potential energy. Okay, but soot, okay, let's look at the soot. 5 minutes, okay. Let's look at the soot. So take optical window, insert it into the chamber, and in a longer or shorter time, you have a deposit like those. And then you can use all the usual means characterizing thanks to infrared Raman and also electron microscopy. And this different diagnostics allows to get into the nanostructuration of the soot. And what I will show you now is that the position of the bands, famous aromatic infrared bands at 6.2 and 7.7 are actually not always at the same place. Probably you know that. It has been the basis for a classification of the astronomical bands shown in red here, the band centers, in classes, class IA, class B, class C. And as the 6.2 moves, the 7.7 moves also to longer wavelengths in each case. And what we have been able to correlate by looking at the soot particles collected in that way from the flame is that it's possible to recover all these class B, class C kind of positions, but we are not quite forming the class A, which means that it's less like a free-flying PAH in a way. Okay, so you can think what you want, but there is some interesting. Okay, these are images, and if you also we can correlate the spectral observations to the nanostructuration, thanks to Raman as well. And in a way, this is a model proposed by Emmanuel Dartois and co-workers for the hack, for the amorphous carbon hydrogenated. And you can see some kind of resemblance between this and soot properties. So, can I use a few more minutes to?
How much time do you need?
10, maybe 5, 10, 5, 5. Let's 5. Okay. In a different experiment, some years ago, we have been doing experiments on the photo-induced chemistry of coronium clusters. It's already a large molecule, but not only it's a large molecule, but you put a number of them together, packed by Van der Waals interaction, and shine a laser and see what happens. Whether or not it has some connection to the rest, that's chemistry that tells it. But the idea of this pH clusters has been already put forward. You have seen that slides before. It comes from the decomposition into 3 kinds of spectra. This was done in collaboration with mainly Martin Schmidt at the Laboratoire Aimé Coton, with this setup here. It's a high-resolution reflectron, which was transferred from Stuttgart, and we have a heater in that part, a crucible, and low temperature liquid nitrogen cooled chamber around, and this is enough to form the clusters. They go out and then ionized. They can be ionized in that part with a discharge here, but you can also ionize them directly with a laser here. Okay, and you see, you analyze mass spectra. This is one of these mass spectra. Mass of coronium is 300. It's very useful to recognize. 6, 1, 2, 3, 4, 5, you can count. And with, for instance, when you are here, you have an object which contains not less than 500 carbon atoms, which is a kind of very large, and whether is this object holds by itself, like between graphene sheets in graphite. Okay, new products are observed, are formed under this laser excitation. It's an excimer at 308 4 eV. You see that here, this is a monomer peak. This is a dimer. The strimer is right here. And you see that there are a number of other peaks which appear in that range between 300 and 400. If you make a zoom, you see these same things, but you also see that starting from the dimer and higher masses, you also have a number of features. Then if you look at the mass separation, of course you have isotopic classical pattern plus just a little dehydrogenation here, for instance, as well as here. If you look at the mass differences, you see this is a methylated coning, methyl coning. But otherwise, you see 26, 24, 24, 24. 24 is 2 carbon atoms. 26 is with 2 hydrogens as well. And then you don't know the structure, but you can start to speculate. And if you look at this, this one here, there is only a single catacondensed a pH that can be can correspond to these peaks. That's Ovalene. So there is possibility that Ovalene has been synthesized. Then you can compare the differences in the different peaks, starting from the mass 300 or 600 or 900. And you see the similar pattern. It's not too much of a surprise. We have information. These peaks are broader than these ones because of recoil, because there is some monomer units evaporated, of course. And now the question is whether is this what's the structure of all these mass peaks behind? One thing which could work is first substitution by a vinyl radical, and then add more C2, like in cumulin kind of chains. But when this such a chain is long like that, it should be very mobile, and at the time form a new ring. Okay, that's the kind of thing we are thinking about. Of course, it needs theoretical work to better understand. Okay, one can find assignments on the main peaks with, in that case, only one pericondensed. Other ones, these are other ones that have several possible assignments. Okay, skip that. Get to the conclusion. So, large cold coronary clusters have been formed. Interesting photochemistry takes place. It may be relevant at the border of dense clouds. after that, I wish to finish to thank my co-workers in the team in Orsay. The one with the circles have the most contributed to that, and other people at the Institute of Astrophysics, Special Astrophysics in Orsay, and people at PLAG and support. Thank you very much.
Thank you. Time for a couple of rapid-fire questions.
So this last experiment you showed using a 308 nanometer laser, do you know how many photons?
How many photons were absorbed?
Yeah, do you know like is the power dependence of the?
No, we don't have the power dependence.
But it must be multi-photon.
We did change the energy of the pulse, but basically not quantitatively. If you do only small energy, we just get the beginning of the products, and if you put more energy, you form more. You go to larger masses.
Any other questions? If not, one.
Yeah, go ahead. Philippe, when you were able to identify all of those PAHs and rule out anthracene and so on, I mean, obviously those spectra are pretty warm, right?
They are about room temperature.
Yeah. So
that's something I didn't tell, but
how exactly did you make the identification? Did you have to model cold spectra, or could you obtain
no.
spectra?
We used as far as possible as reference spectra taken at room temperature.
Okay.
And of course, one has to take into account most of them are absorption spectra, and you have to take into account the fact that in two-photon ionization, you have a limited. You spend some time in the excited state, intermediate excited state, before ionization, and it's reducing the efficiency the same way because of intramolecular processes like in quenching fluorescence.
Quick? Yeah, very quick. So since in Typenstein they showed recently that it's highly unlikely to have actually PAH clusters contributing to Soot formation. But you guys are still doing experiments with PAH clusters. So do you think that they are wrong, or why are you still doing these experiments?
What?
Even Sims, so Sims and Typenstein, they showed experimentally and theoretically that it's highly unlikely that clusters of PAHs are important in combustion flames.
Yeah, no, of course it's
right.
No, it's different starting conditions, and you put energy in this system. You know more or less what is the structure. At least you have theoretical works show that they should pile up to 5 or 6, and then grow another pile, different orientations. But if you put energy in that, we think that first, what is known, I mean, the absorbing part, the chromophore in these clusters, where the energy is put in, is one monomer unit, of course. And it is known that when you do that on a only monomer isolated molecule, you lose hydrogen, you dehydrogenate one or two. One first, and the second one is then more easily. This then create a site, a reactive site, and things may start that way. That we don't tell. It's similar to Soot, but in a way there are maybe chemical routes which are the same in both kinds of experiments. That's the idea.
Maybe I should have said also a quick answer as well. Thank you. Okay, thanks.